Okay, so we talked before in class about how if we wanted to find the limit of this sequence, we could compare rates of growth. With, we talked about comparing rates of growth, and the idea was the numerator has quadratic growth, the denominator has exponential growth, and exponential growth is faster than quadratic growth or any polynomial growth. So this limit would be equal to 0. Now we can formalize that by using L'Hopital's rule. So if we let f of x, so let's make this a little bigger here. So we're going to let f of x equal x squared over 2 to the x minus 1. Then we need to consider what's the limit as x goes to infinity of f of x. Okay, so that's going to be equal to the limit as x goes to infinity of x squared over 2 to the x minus 1. And we can use L'Hopital's rule to say, or I think I usually do LH, use L'Hopital's rule to say that this limit is the same as the limit as x goes to infinity of 2x over natural log of 2 times 2 to the x. So here I'm taking the derivative of the numerator, and I get 2x, and the derivative of the denominator gives me natural log of 2 times 2 to the x. Okay, and now we still need to apply L'Hopital's rule again because our numerator goes to plus infinity and our denominator goes to plus infinity as x goes to infinity. So we still have a limit that is in indeterminate form. So we'll have this as equal to the limit as x goes to infinity of 2 over, now I still have my natural log of 2, but I'm actually going to square it when I take the derivative of the denominator. Now we no longer have an indeterminate form because my numerator is going to 2 and my denominator is going to plus infinity. So my limit is going to equal 0. And this is exactly what we would have found using rates of growth. Okay? All right, so we get that limit is equal to 0. Let's look at the second example here. Find the limit a sub n is equal to 3 plus negative 1 to the n. Now here, what I'm going to do is I'm going to write out a few terms because it wouldn't make sense to try to use L'Hopital's rule. This is it's not a product of two functions. There's nothing I can do to manipulate this. So I'm going to write out a few of the terms. So it looks like a sub 1 is going to be 3 plus negative 1 to the 1, which is just going to be 3 plus negative 1, which is just going to be 2. A sub 2 is going to be 3 plus negative 1 squared, which is going to be 4. A sub 3 is going to be the same as a sub 1, right? Because we'll have 3 plus negative 1 cubed, and that's going to be 3 minus 1, which is going to be 2. So I see that our terms are oscillating. So our terms are oscillating 2, 4, 2, 4, 2, 4, so forth and so on. It'll be 2 if n is odd, and 4 if n is even, right? So the limit does not exist because the terms are oscillating. So that would be my final answer. Limit as n goes to infinity of a sub n does not exist, oscillates. Sequence oscillates. All right, and now let's have one more example here. What about this one? Find the limit a sub n equals n divided by 1 minus 2n. Now, you can look at this and say that the limit as n goes to infinity of n over 1 minus 2n is indeterminate form, which it is because the numerator is going to plus infinity and the denominator is going to negative infinity. So infinity over infinity, indeterminate. So you might think, oh, let's use L'Hopital's rule. But actually, you don't need to use L'Hopital's rule. So we can, looking at this, limit as n goes to infinity, n over 1 minus 2n is going to be the same thing as 1 over n minus 2. Now, how did I do that? I just divided or multiplied the top and the bottom by 1 over n. Right? So my numerator became 1, and my denominator became 1 over n minus 2. And now I can say my numerator is tending to 1 as n approaches infinity, and my denominator, right, the 1 over n is going to tend to 0. The 2 is going to tend to 2. So I should have 1 over negative 2, or negative 1/2. Okay? So lots of times, you can determine the limit without using L'Hopital's rule. L'Hopital's rule will work. So if you want to use L'Hopital's rule, you can. I'm just saying that you don't have to use L'Hopital's rule in every instance. Okay. And I think there's one more example. Yeah, here we go. Which is to find the limit as n goes to infinity of 1 plus 1 over n to the power of n. Okay. Now, this is definitely an exponential form, indeterminate form, because the 1 over n is going to 0, and the n is going to plus infinity. So this would be of the form 1 to infinity. Do you see what I'm talking about here? So the inside here is tending to 1, and the exponent is tending to plus infinity. So we get 1 to infinity. This is indeterminate form. And the key is, do you remember what to do? When you have an indeterminate of this form. Here's what we do. We're going to insert or introduce a natural log, because the natural log is going to bring that exponent down to the bottom. So let's look at how this actually plays out. Okay, so if we have the limit as n goes to infinity, 1 plus 1 over n to the n. We can write this as a limit as n goes to infinity. And now, instead of 1 plus 1 over n to the n, we could have e to the natural log of 1 plus 1 over n to the n. And we're using the log property, that e to the natural log of anything, say smiley face, is equal to smiley face. So if I'm starting off with smiley face, I can rewrite it as e to the natural log of smiley face, assuming that smiley face is in the domain of natural log, which here it will be, because 1 plus 1 over n is always going to be a positive number. In the domain of natural log, any positive number. Okay, now that I've got this, right, and this is actually the natural log of all of this stuff, so now that I've got this, I can take my exponent and bring it down front. Okay, so I've got equals the limit as n goes to infinity, e to the n times natural log of 1 plus 1 over n. Okay, now we're in a situation where the n is going to be tending to plus infinity, and the natural log of 1 plus 1 over n is going to be tending to natural log of 1, which is equal to 0. So we essentially have infinity times 0, and we know what to do with that. So I'm going to rewrite it as, I'm still keeping my e in here, and the reason why I recommend continuously writing your e is so you don't, number one, because these terms are actually equivalent to each other, these limits are equivalent, so you're writing true mathematical statements. And number two, you don't forget to exponentiate at the end of taking your limit. So you'll see me, I'm writing e, 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 I keep writing this e, even though most of the work that I'm doing is in the exponent. So let's see here. So we'll have natural log of 1 plus 1 over n divided by 1 over n. And so now how did I do that? I can go over here to the side and show you. We said this n times natural log of 1 plus 1 over n. That's the same thing as natural log 1 plus 1 over n divided by 1 over n. And so how does that work? This n is the same as 1 over 1 over n, right? So n is 1 over n. So multiplying by n is the same as dividing by 1 over n. Okay, and the reason, of course, for doing this is because now my denominator is going to 0 and my numerator is going to 0. And I can, due to the continuity of exponential functions, figure out this limit by finding the limit of the exponent. So this is going to be equal to e to the limit as n goes to infinity of the natural log of 1 plus 1 over n over 1 over n. Okay? And this limit is going to be, right, because again I can use L'Hopital's rule because I've got the indeterminate form of 0 over 0. So I can rewrite this as the derivative e to the limit as n goes to infinity. This is by L'Hopital's rule. Now I need the derivative of the denominator. That's, let's see here. So a quick way to do this is if I have, let me actually scooch over to a new page. Add a page below. Okay. So if I want to know the limit as n goes to infinity of the natural log of 1 plus 1 over n over 1 over n. Okay. So I'm going to look at the limit as x goes to infinity, natural log 1 plus 1 over x over 1 over x. And this, by L'Hopital's rule, is going to equal the limit as x goes to infinity. I need the derivative of the denominator. So x to the minus 1, the derivative of that is going to be negative x to the negative 2. So negative x to the negative 2. And I need the derivative of the numerator. So natural log of 1 plus 1 over x. And I'm going to use chain rule all day long. So I have 1 over the inside, which is 1 plus 1 over x, times the derivative of the inside, which is going to be negative x to the negative 2. Okay, so I have 1 divided by 1 plus 1 over x times negative x to the negative 2. And this term and this term will cancel out. So my limit as x goes to infinity, that is going to go to 0. So my limit is going to actually equal 1, right? Because I have 1 over 1. That's my limit. So now, back here, this limit here, we determined that this limit was equal to 1. So by L'Hopital's rule, this is equal to e to the 1, which is just equal to e. All right. So the bottom line here is that when you have 1 to infinity, it is indeterminate. You have to use L'Hopital's rule. Okay, so 1 times 1 times 1 times 1, right? 1 times 1 times 1 times 1 times 1 times 1 times 1. And you want to take the limit as n goes to infinity. It's not equal to 1 necessarily. Maybe it's equal to 1, maybe it's not equal to 1. Maybe it's plus infinity, maybe it's not plus infinity, right? You have to actually introduce the e in the natural log And then introducing that natural log will bring that plus infinity down and allow you to really analyze the behavior of your sequence. Okay, that's it.